Hello, welcome to ePathshala. In this module, we'll be deliberating on synthetic fibers. This is Dr. B.A. from the Department of Textile Technology, AC Tech, Anna University, Chennai. Introduction about synthetic fibers. Textile fibers, both natural and manufactured, have been used to make clothing for several thousand years. Manufactured fibers are fibers produced from chemicals and can have superior properties to natural fibers that are grown or developed from plants and animals. The production of manufactured fibers is an example of how industrial process has contributed to modern life. Manufactured fibers are those materials that are made by human beings by drawing and orientation of polymers that are commonly called fiber-forming polymers. A manufactured fiber, also referred to as synthetic fiber, is a chain of small units, a chemical substance joined together to form a large single unit called a polymer. Polymer is a Greek word, poly meaning many and mer meaning units or parts. Polymers were accidentally synthesized. However, as more and more applications were discovered, polymers have penetrated into all fields of applications in large volumes. Polymers may be broadly classified as natural and synthetic polymers. Classification of fibers. Fibers are generally classified as a natural fiber and man-made fibers. Natural fibers are broadly further classified as the animal fibers and the vegetable fibers. Animal fibers from silk, from wool hair, and the vegetable fibers from the seed of the cotton, and from the bark of the plants such as the flax, hemp, jute, kenaf, and rami, and from the leaf such as the albaca and sisal fibers, and the fruit fiber which is called as the coir. Further, the man-made fibers or the synthetic fibers are broadly classified as the artificial and the synthetic fibers. The artificial fibers being classified as the cupro fiber, viscose or the viscose rayon fiber, modal, polynol, diacetate, acetylated acetate fiber, acetate fiber, triacetate fiber, alginic, protein, elastodine, and tensile fiber. They are classified as organic, which is the acrylic, chlorofiber, elastane, fluorofiber, modacrylic, polyamide, polyester, polyethylene, polypropylene, polyvinyl, and these are further classified as to inorganic fibers such as from the metals and the boron fibers and other fibers like the textile, glass, carbon, and others. Synthetic fibers are prepared from the respective monomers by the process called polymerization. Polymerization is a chemical process that prepares and combines the components of fiber-forming substances. Polymers are macromolecules built up by linking up large number of small molecules called monomers. Polymerization can be accomplished by the following ways. The first one is the step growth polymerization. It is also called as the condensation polymerization. And the second technique is the chain growth polymerization, also called as the additional polymerization. Step growth or the condensation polymerization generally proceeds in distinguishable steps with the possibility to carry forward the chain propagation indefinitely. In synthesis of polymers, bifunctional or polyfunctional reacting molecules are essential. Further, in this type of polymerization, a small byproduct like a water or other low molecular weight products are eliminated. Chain growth or addition polymerization processes are commonly characterized by the chain reaction mechanism, and the chain propagation may take place by a free radical mechanism or ionic mechanism. Here, the reactive double bond of the monomer is activated and opened up to form new bonds. The chain growth polymerization is characterized by three steps. That is the initiation process and the growth of the polymer and the termination reaction of the polymer. Polymers are broadly classified as the following ways, that is based on the structure of this polymerization method and the response technology and the chemical constituents and catalysts. These are the different ways in which the polymers could be catalyzed. Now, based on the structure, the polymers are further classified as the physical. Physical, it is classified as the crystalline, could be semi-crystalline or amorphous in nature, and chemically it could be linear polymer, branched polymer, cross-linked polymer, interpenetrating polymer, or stereopolymer such as the isostatic, atatic, and symbiotic. And based on polymerization methods, it is classified as additional, condensation, or special type of polymerization. And with respect to the response technology, it is called as a thermoplastic or thermosetting polymers. Then further, based on the chemical constituents, it is either called as a homopolymer. It could be a copolymer, which could be alternating, which could be random, or it could be a block, or even could be a graft. Further, it is called as a composite, where the poly blend or plastic alloy. And then based on the catalyst, it is classified as a Ziegler-Natta catalyzed or multi-metallocyanate catalyzed metathesis. So these are the three ways with respect to the catalyst. Okay, in natural polymers, the fiber forming substance, that is the relevant long chain polymer molecules, has been made by nature in a ready-made fibrous form such as cotton, flax, wool, and silk fibers, etc. In synthetic fibers, on the other hand, are those fibers in which man has generated a suitable fibrous form for the formation of the fiber. The performance properties of synthetic fibers are determined by the fiber structure, which in turn depends on the processing technique and the physical and the chemical structure of the polymer. Synthetic fibers are classified as polyamide fibers, polyethylene fibers, polyolefin fibers, polyurethane fibers, polyvinyl derivatives, and other miscellaneous synthetic fibers. Now let us go into the deliberation of the polyamide fibers. The polyamide fibers are characterized by the recurring presence of NHCO amide linkages in the chain backbone. Synthetic polyamide fibers are derived by two ways. The first one is through the interaction of a diamine and dibasic acid by the condensation reaction of, example, hexamethylene diamine and adipic acid. And the second technique is the ring opening polymerization of the lactam, that is the self-condensation of caprolactam. After the end of World War II, two varieties of nylon fibers were produced, that is nylon 6 and 6,6, which are established as the most important synthetic fibers in the textile industry. Nylon 6,6 is spun by condensation of hexamethylene diamine and adipic acid, whereas nylon 6 is spun from this self-condensation of caprolactam. Both these fibers are produced as monofibers, multifibers, or in the form of a tow, and is also staple spun virtually to suit all textile requirements. Nylon are smooth surfaced fibers produced by melt spinning, normally in a round cross section. The fibers are available in dull, semi-dull, or bright lusters. They possess exceptional mechanical properties, including high breaking strength, high strength to weight ratio, excellent recovery from deformation, and good flex and abrasion resistance. Its specific gravity is about 1.14 grams per cubic centimeter. In recent years, a number of new polyamide fibers have assumed commercial importance and end users of nylon fibers. Carpet and upholstery industry use the significant amount of monofilament in the production of carpets and upholsteries. Then the apparel industries, a large amount of fiber is being used in the production of lingerie, swimwear, sportswear, hosieries, socks, gloves, and other textile materials. As far as the industrial applications are concerned, nylon fibers is a choice material which is used in tire cords, hose, conveyor belts, fishing nets, twines, ropes, tents, and reinforced plastic materials are also manufactured using nylon fibers. Now we'll go into the deliberation of polyester fiber. Polyester fibers are long-chain linear polymers made by a condensation reaction between an acid and an alcohol, in which the linkage occurs through the formation of an ester group. Synthetic polyester fibers are derived by the interaction of a dibasic acid with a dihydric alcohol. First, commercial polyester was spun from polyethylene terephthalate, that is PET, example terylene. Polyethylene terephthalate is made by the condensation reaction of ethylene glycol with dimethyl terephthalate. PET fibers are produced as tow fibers, staple fibers, mono and multifilament fibers, generally in a circular cross section and a range of brightness and luster, with wide range of properties to suit the specific requirements. The specific gravity of polyester is around 1.38 grams per cubic centimeter, and it absorbs a very small amount of moisture at about 0.4% in standard conditions. It has good resistance to acids, dilutors, alkalis, oxidizing and reducing agents. Polyester fibers are smooth, rod-like, have circular, trilobal or multilobal cross-section. They show good all-round elastic recovery under compression, tension and shear. Have high modulus and are dimensionally stable. Low moisture regain and low creep. So some of the end-use application of polyester fibers are: polyester fibers have made their way into almost every type of apparel end uses, such as suitings, dress materials, floor coverings, industrial applications such as conveyor belt, fire hose, sailcloth, ropes, fillings, tire cords, electrical insulation, sewing threads, and etc. Next, we'll discuss about the polyolefin fibers. Polyolefin are fibers manufactured by long-chain polymers composed of at least 85% by weight of polypropylene, ethylene, or other olefin units. They are spun from polymers or copolymers of olefin hydrocarbons, namely ethylene, and products of naphtha cracking. The two most important polyolefin fibers are polyethylene and polypropylene. Olefins undergo additional polymerization. Polyethylene fiber. Polyethylene molecules are generally branched, and the degree of branching depends upon the condition of polymerization. The polymerization of double bond ethylene proved a difficult task. However, during the World War II, the low-density polyethylene, also called as LDPE, were developed and put to some use. Nonetheless, its low melting temperature and low strength were the limitations. This paved the way for the development of high-density polyethylene, employing the Ziegler-Natta catalyst. High-density polyethylene, also called as HDPE, is by large a linear polymer with a high degree of crystallinity in the range of around 80 to 98%. Both types of polyethylene may be spun into fine denier, multifilament, monofilament, and a range of diameters in round, flat, or oval cross-sections. Polyethylene fibers cannot be dyed effectively using the regular dyeing techniques. As such, it is dope dyed. The specific gravity of low-density polyethylene is in the range of 0.92, and for the high-density polyethylene, it is about 0.95 to 96. Polyethylenes are highly resistant to acids, alkalis, and to most common organic solvents. Now, brief about the end-use applications of polyethylene fibers. The properties of polyethylene are largely influenced by the spinning and subsequent stretching, and which influences the orientation of the molecules. Major applications include ropes, twines, tows, nettings, upholstery materials, filtration fabrics, blinds, awnings, woven sacks for packaging, and bags for carrying. Low cost, non-toxic lightness, rot resistance, flexibility, ease of handling, resiliency are some of the advantages of polyethylene. Now we'll go to the next olefin fiber, that is the polypropylene. In the early 1960s, the polyolefin were regarded as fibers with immense potential, importance comparable to polyamide and polyester. Polypropylene fibers can be melt spun like other synthetic fibers. Polypropylene molecules consist of zigzag three-dimensional chain structure with long chain of carbon atoms attached with methyl side groups. Polypropylene fibers offer higher temperature resistance, high strength, stiffness, and optimum crystallinity. The spinning and processing condition have a great influence on fiber properties. The fibers are produced in the form of staple fiber, tow, mono and multifilament yarns and slit films. Polypropylene is inert to a wide range of chemicals and has excellent resistance to acids and alkalis. End-use applications of polypropylene fibers. Polypropylene being the lightest fiber with its specific gravity around 0.9 grams per cubic centimeter, both polypropylene and polyethylene are lighter than water. Its applications include blankets, sweaters, upholsteries, knitwear, conveyor belts, tire cords, tufted carpets, fishing nets, twines, ropes, sewing threads, woven sacks, and packaging and other materials, etc. We'll go to the next fiber, which is the polyurethane fiber. Polyurethanes are the segmented polyurethanes. It's called as the elastomers. Are man-made fibers in which the fiber-forming substance is a long-chain synthetic polymer composed of at least 85% of segmented polyurethane. Linear polyurethanes are polymers with an interunit linkage of HNCOO, which is the urethane linkage, made by the reaction of diisocyanate with a diol or a glycol. Elastomeric polyurethane have a structural feature of block copolymers known by the generic name spandex. In the block copolymers, the long flexible segment of the molecules are joined by urethane linkages to the short stiffer segment. They are formed by the chain extension reaction of low molecular weight hydroxy-terminated polyether and a diisocyanate. Okay. The elastomeric fibers are those which display elastic characteristics, that is, they stretch to several times to their original length and will snap back quickly to recover their original length. Segmented polyurethanes may be spun in the form of mono or multi-filaments. Its specific gravity is in the range of 1.2 to 1.25 grams per cubic centimeter. Its resistance to alkali solvents and common chemicals is generally good, but its resistance to acids varies depending on the type of spandex. Now let us look into the end-use application of polyurethane fibers. Segmented polyurethane filaments could be used as a base filament, covered yarn, or as a core yarn or core-twisted yarn. Major applications include garments, swimwears, hosiery garments, power nets, lace for decorative purpose, co-spun yarns for sewing threads, and other application. Let's go into the deliberation of polyvinyl derivatives. Polymers containing the vinyl group CH2 double bond CH commonly undergo addition polymerization without elimination of water or other materials. Modern polyacrylonitrile based fibers are basically copolymers of acrylonitrile with suitable comonomers. They are now produced under a variety of trade names. Polyacrylonitrile fibers are subdivided into two classes based on the properties of acrylonitrile as. Acrylic fibers are manufactured from polymers comprising of at least 85% by weight of acrylonitrile repeating units. Monoacrylic fibers are materials manufactured by polymers comprising of at least 35 to 85% by weight of acrylonitrile repeating units. The polyacrylonitrile fibers are found to be strong resistant polymers, difficult to dye. 100% PAN fibers are usually highly crystalline. And some of the application of polyvinyl fibers are acrylics have good photostability and are stable to dilute acids and alkalis. They are used in filament or spun yarn form. A specific gravity is about 1.16 to 1.18 grams per cubic centimeter. Acrylic fibers are resistant to mild acids, alkalis, and most common organic solvents. Strong acids and alkalis attack the fibers. Acrylic fibers used in making carpets, knitwear, sportswear, blankets, dress materials, draperies, furnishing, non-woven and industrial fabrics. Mod acrylic fibers have excellent resistance to acids, organic solvents and alkalis. Its specific gravity is relatively high at 1.37 grams per cubic centimeter. Its applications include pile fabrics, knitted goods, industrial fabrics, carpets, draperies and upholsteries, etc. Now let us go into the deliberation of some of the miscellaneous synthetic fibers which have been manufactured. So for the first variety which comes to mind is the carbon fiber. The development of carbon filament began early in 1850, and in 1880 carbon filament was patented for use in incandescent lamps. One of the popular techniques used in carbon fiber production is the controlled oxidation of polyacrylonitrile or PAN precursor fiber, followed by high temperature carbonization in an inert atmosphere to completely remove the nitrogen and hydrogen atoms from the polyacrylonitrile chain, leaving behind the carbon molecules or the carbon fiber. This carbonized carbon fiber is further heated at an elevated temperature of a range of 1000 to 3000 degrees to axially organize the crystalline structure. The final heat treatment is very important in producing high modulus carbon fibers. Carbon fibers are black in color, highly inert to chemicals, solvents and oxidizing agents. They are smooth surfaced with circular cross section and have good luster. The density is in the range of 1.75 to 1.90 grams per cubic centimeter. They are characterized by high strength and stiffness. Carbon fiber applications include specialized composites for space vehicles, aircrafts, automobiles, sports goods, marine applications, submarines, pressure vessels, and protective clothing, etc. The next miscellaneous fibers will be glass fiber. Glass is essentially manufactured from sodium, calcium, silicate and other ingredients, namely magnesium, alumina, potash, soda, boric acid in different percentages. The ingredients are charged in the furnace where they are fused at high temperatures to form glass filaments directly or formed into marbles. Glass is manufactured in a large variety of composition, two main types being E and C glass. E glass have good electrical and high heat resistance, whereas the C glass has good corrosion resistance to a wide range of acids, alkalis and chemicals. The specific gravity of glass is about 2.54 grams per cubic centimeter. Glass fibers are resistant to almost most solvents, acids, alkalis. Glass is not a good conductor of heat, as such use it for thermal and electrical insulation. Glass fibers are produced in continuous filament form or in the short staple fiber form. Applications of glass fibers include reinforcement in plastics, industrial filter fabrics, tire cords, belting fabrics, etc. Glass fiber in the form of chopped strand or roving are extensively used in reinforcing fibers in constructing aircraft components, ship hulls, automobiles, structural sheets, roofings, filter cloths, optic fibers, and fireproof fabrics. The next miscellaneous fiber is the alumina silicate fiber. Alumina silicate fibers are manufactured by the fusion of aluminum oxide and silicon dioxide. These fibers are used for insulation in the temperature range of 450 to 1300 degrees Celsius, where the regular glass, asbestos and mineral fibers become ineffective. They are typically produced as short or long staple fibers and have good resistance to most acids and dilute alkalis. The specific gravity of aluminum silicate fibers is 2.72 grams per cubic centimeter and are predominantly used in high temperature insulations, including electrical, thermal insulation, gaskets, filter conveyors, engine blankets, joint packing in furnaces, engine silencers, gas filters, castable pressure vessels, fire-resistant products, missiles, rockets, filtration of radioactive particles. We'll talk about the next miscellaneous fibers, which is the metallic fiber. A manufactured fiber consisting of metal filament, plastic coated metal or metal coated plastic or core metal filament. Metallic filaments are produced by drawing ductile metal filaments into strands. Metallic fibers have a long history and have been produced since the dawn of civilization for ornamental applications in brocades, damasks, and carpets. Today, metallic yarns primarily consist of aluminum filaments covered with thermoplastic or polyester films. These yarns may not be very strong, but their strength is sufficient to withstand the wear and tear during the process of weaving. They are mostly used for decorative applications in upholsteries, carpet industries, applications include medical application, fiber reinforcements, some of the dress materials, table linen, footwears, vests, jackets, curtains, and packaging materials. So these are some of the applications for which the metallic fiber is a material which is used only with the objective of decorative purpose. Some of the module on the synthetic fibers. Let us briefly look into the things which were introduced in this model. So we started with the introduction of the textile fibers and how broadly the textile fibers have been classified into natural and synthetic fibers. And more emphasis has been placed on the synthetic fibers and the way the synthetic fibers have been polymerized, that is the step polymerization and the chain growth polymerization. And then we went on to talk about the different fibers, classification based on the physical, chemical, and then based on the method of polymerization. Then we talked about the response technology, and then we talked about the chemical constituent, and then based on the catalyst, type of catalyst used in the manufacture of synthetic fibers. Then the synthetic fibers in which we dealt with in detail. The scope in this module, the scope is only limited to the classification and uses of this polymeric fibers. So not much has been dealt with respect to the manufacturing aspects. So what has been done is we have dealt with the polyamide fibers, the nylon 6 and nylon 6s, their application, and some of the brief properties which are essential to take a decision. Then we have deliberated on the polyester fiber, followed by the polyolefin fiber, where we talked about the polyethylene and the polyethylene fiber and polypropylene fiber. Then we went on to talk about the segmented polyurethane fiber, which is an elastomeric fiber which is used as an elastane, and the applications of the elastomeric fibers. Then we discussed about the polyvinyl derivatives, and then we went on to discuss some of the miscellaneous synthetic fibers such as the carbon fiber, the glass fiber, the aluminum silicate fiber, and the metallic fibers which have been used from quite some time for the purpose of ornamental. So the scope of this module is not to deal with the manufacturing aspects, but just to introduce the textile graduates to the classification and uses of some of these popular synthetic fibers which is being used in the textile industry.